In this video, we're going to look at a few more advanced algebra parent functions. Now, if you're not familiar with what parent functions and their representations are, you might want to first go back and look at parent functions and representations videos. And also, you may want to look at the basic functions, parent functions, which you can find in basic algebra functions, another video on that. But if you're ready for this one, let's take a look at a few more of the advanced parent functions and their characteristics. We're going to start with y equals square root of x. Now remember that a parent function is the simplest form of a function within a function family. And in this case, that would be the function family that contains the square root of x somewhere in the function. If it has anything added or multiplied or anything else in the function, it's not the parent. It's not in the simplest form. As we usually do with these, let's take a look at table of values here. Now, I carefully picked the x's 0, 1, 4, and 9 because I wanted numbers that I could take the square root of and they would come out to integers. Notice that I didn't pick any negative numbers because as I look up here, if I put a negative number in for x, it would be trying to take the square root of a negative number, which I can't do and get a real answer. So I only want to pick numbers that are allowed, and in this case starting at 0. So if I go ahead and fill this table in for the y values, right here, I get 0, square root of 0 is 0, and then I get 1, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. Hopefully you remember what square roots do. It's what number you can multiply by itself to get the value of x. Now one thing we do when we're dealing with square root functions is we don't look at the negative answers. If you'll recall, square roots actually have two answers. The square root of 4 is actually 2, but also negative 2. We only use the positive or principal or primary root when we get these answers because we want it to represent a function. If we represented positive and negative, if you recall the definition of function, any value of x must get only one value for y, and that would be giving us 2. So we're only going to use the positive version in order to keep this defined as a function. Now let's go ahead and plot these up here on the graph and see what they're going to look like whenever we graph them. So there's the dots or the graph that we're going to do, and I'm going to connect them with a line, which I put an arrow on the end to show that it continues on. And there's the basic shape of the square root function. You'll notice that it's basically the parabola turned on its side without this bottom part. The bottom part is what we left off because we didn't use the negative numbers. If we had, it would have violated the vertical line test, which says if we draw a vertical line through a function, it can't go through 2 points at one time, and it does. It goes through a point here, and it goes through a point here. So I don't want to use the bottom half. I only want to use the part right here in blue. And that is my square root function. That's the parent function of it. What are the key characteristics? It starts at 0, 0 right there. You go over 1, up 1, square root of 1. You go over 4, up 2, square root of 4. You go over 9, up 3, and then you continue that pattern. You have to go out to 16 on x to get the next one, which would be 4. And that is my square root function. Noticing that the parent function never goes over here because you never have negative x's. If you try to put those in, you don't get real answers. So we don't use negative numbers for x. They begin at 0. So keep that in mind. That's the square root parent function and its characteristics that you need to know. Let's take a look at another one here. X cubed to the third power. Again, function family that contains x with a cube, where the largest exponent is 3. The x cubed family has some similarities to the x squared family, but then there are also differences. Let's again take a look at a table of values here and see what we get. Again, I just picked numbers, but I tried to pick numbers that are going to work well. A couple of negatives, a couple of positives, and 0. These are pretty easy. So whenever I complete this table, here's what it looks like. Negative 2 times negative 2 times negative 2 is negative 8. Negative 1 times negative 1 times negative 1 is negative 1, and so forth. That's where the table came from. And if I plot those values and connect them with a line, there's half of it. That's actually the positive side. See how it looks just like the x squared, except it's a little bit narrower and skinnier because it still starts at 0 there. Goes over 1, up 1, but at 2 it goes all the way up to 8 instead of 4 like the quadratic did. But look what happens when I plot these negative values right here onto the graph. Now I have this bottom part down here, and this is different. The parabola on a square went up like that, but on this cube it goes down because you do get negative answers. When you do something cubed, you can get negatives. When you square something, it will always get positive values for y. So key characteristics of x cubed, again, crosses at the origin 0, 0, over 1, up 1, but over 2, up 8. So that's a good way to recognize that it's cubed on the positive side as opposed to x squared. And then when you look at the negative side, now you go over 1 to the left, negative 1, and down 1 this time because you can get negative values for y. And so this time, this part of the graph right here goes down instead of up. So those are the key characteristics that allow you to recognize x cubed. Remember, we want to recognize the parent so that we can look at other graphs with a similar shape, know they belong to the family x cubed, and realize some transformation has happened to them. And those are transformations that we can learn and be able to write the equation from that transformation that's happened. It all starts from recognizing the parent. Let's take a look at another one that goes along with that, that's an advanced, more advanced parent function, and that is the cubed root of x. Now, this one is kind of interesting because it is derived from x cubed, as was the square root from x squared. So let's see, let's take a look at a table here. Again, I'm going to be a little picky about the values I pick over here because I want to make sure that I can take the cubed root of them. Remember, a cubed root is what number can you multiply by itself 3 times to get whatever the value of x is. So the cubed root of negative 8 is negative 2. 2 times 2 times 2, and it's negative, will give you that. So here's that table completed. Negative 2, negative 1, 0, 1, 2. And that's my table, and go ahead and graph it and attach it with a line. Here are the positive numbers graphed. So that's from here down. Notice that it looks like this, only now it's laying down and going along the x-axis. It also looks like the square root function, except it's a bit flatter. The square root function would have reached 2 at 4, right there, whereas this one doesn't reach 2 until it gets all the way over to 8 because of the cubed root here. And then when I add the negative numbers, much like happened with x cubed, this time the numbers do go negative, and it makes sort of a flattened out S shape as we look at it. And you can see that the negative part over here is down at the bottom instead of nothing that we saw whenever it was the square root of x, because we couldn't do negative numbers with square roots. So characteristics, 0, 0 is the crossing spot, square root over 1 up 1 over 8 up 2, and the same thing to the left, negative 1 and down 1, and then negative 8 down 2. Those characteristics make up this cubed root of x, and you should be able to differentiate that then from the square root because it goes to the left, meaning you can have negatives, and it's flatter because you've got to go all the way over 8 in either direction to actually go up or down 2. One last one I want to look at as an advanced function is the rational parent. Whenever x is in the denominator of the equation, this is the simplest version. Again, I'm going to do a table, and that table of values is going to be a little more complex. First of all, I did this. When I do negative 4, 1 over negative 4 is negative 1/4, then negative 1/2, then negative 1, 1 divided by negative 1. But look what happens at 0. 0 cannot go in the denominator of a fraction. Division by 0 is not legal thing you can do in algebra. So you can't do that 0, so actually it is undefined at that point. So you have to realize it's never going there. You're never going to have a value where x is 0. You're never going to have a point on the y-axis. Let's go ahead and break down the numbers between 0 and -1 a little bit more. I just chose -1/2 and -1/4 to show you that when you do 1 divided by -1/2, that actually comes out to -2. Remembering your rules of division of fractions, you flip the denominator and multiply, which means you're actually multiplying by -2. Same thing with -1/4. And then I did it on the other side. So I put 1/4 in there, multiplying by 4, multiplying by 2 to get 1/2. You notice that these numbers actually are getting larger and smaller along here. So that was important to see. And then I went ahead and finished the rest of the table. 1/1 is 1, 1/2 is 1/2, and 1/4 to get the rest of the numbers in here that I wanted, like that. And let's go ahead and plot this. First of all, I did the ones on the left right here and included these two. Notice that it gets really, really close to the x and the y-axis, but it's never quite getting there. Same thing at the bottom when I plot the other half of them. And join them with lines. It looks like this. It's actually approaching the x-axis and approaching the y-axis, but the graph never reaches that. We call the x and y-axis in this case asymptotes. An asymptote, misspelled that one. An asymptote is actually a line that a graph approaches but never reaches. In this case, the x and y axis. So this has two. It has a vertical, the y-axis, and a horizontal, the x-axis. Again, it's going to be very important to recognize this characteristic when we get ready to transform functions. The characteristics of asymptotes are going to make it much easier to move these around and see where they've moved from. So what characteristics actually made up this rational parent function? First of all, never touches x or y. You can see that the graph approaches x and approaches y, both from the left side and from the right side. The next thing is, believe it or not, we can always look for this right here, the 1, 1, and the -1, -1. That's a good point to realize that's where it actually turns and begins to approach the y-axis on the left, or it turns from approaching the y-axis and begins to approach the x-axis on the right side. Those are two key points that make up the parent function. And again, realizing that will help you to know that something has changed about the function when it gets transformed. Be sure you recognize that the parent function appears in quadrant 3 and quadrant 1, not over here. If you see this in those two, that's okay, but it's not the parent function. That means a negative has been applied to it and it's no longer in its simplest or most basic form. So those are a few of the more advanced parent functions that you encounter in algebra. There's one more video on advanced functions that will take a look at exponential and logarithmic as well as the absolute value function. If you want to take a look at that video, you can find that at MyMathEducation.com. You'll find a lot of videos there organized by topics, or you can go to my YouTube channel at MyMathEducation, and I invite you to do that and to subscribe if you'd like to look at more videos on algebra or other math topics. Appreciate you watching this, and thank you for doing that. Hope you'll come back and look at other videos to help you along with your math education. Thank you again.